हेलो एवरीवन। आज हम लोग देखेंगे ऑर्गेनिक नेम रिएक्शन सीरीज का 6 नंबर रिएक्शन, that is dehydration of alcohols. And remember, dehydration of alcohols is considered as name reaction. तो यहाँ पे जो डिहाइड्रेशन ऑफ अल्कोहल्स होता है वो हम लोगों का मेथड्स ऑफ प्रिपरेशन ऑफ एल्किन्स के अंदर आता है। ठीक है, सो ये है हम लोगों का मेथड ऑफ प्रिपरेशन of alkenes. So let's see what is dehydration of alcohols. So let me write it here. On heating with concentrated sulfuric acid, concentrated sulfuric acid, say sulfuric acid, or phosphoric acid, or on passing their vapors over heated alumina, that is Al2O3, at 350 degrees Celsius, that is 623 Kelvin. Alcohols lose a water molecule to form alkenes. See, all the conditions should be satisfied. That is, you have to heat concentrated sulfuric acid, or you can heat phosphoric acid, or you can pass the vapors of heated alumina at 350 degrees Celsius temperature. Alcohols lose a water molecule to form alkenes. So let us see by one example. Let us say our general format is RCH2. So we can write it as RCHH. Let us say we have a alcohol in this format. Okay. In this alcohol, if you pass concentrated H2SO4 at 623 Kelvin, this alcohol will lose a water molecule. This H and OH will go out. So it will be R C H double bond C H H plus H2. If you take example, let us say in place of R we have CH3. That is, let us say we have ethanol. That is CH3 CH2OH. This is our ethanol, and this ethanol will lose a water molecule. So we can write in this format, that is C H H H and C H2OH. So this H and OH will go out. So in place of that, we will get a double bond. Let us say we have given Al2O3 at 623 Kelvin. Okay. Remember one thing, that if you give Al2O3, you have to give 623 Kelvin, and if you give concentrated H2SO4, you have to give 443 Kelvin. So you will have alkene, that is CH2 double bond CH2 plus water. Okay. Now see, in case of dehydration, that is removing a water molecule, in presence of concentrated H2SO4, the alcohol first reacts with sulfuric acid to form the alkyl hydrogen sulfate, which upon heating loses molecule of H2SO4 to form alkene. Okay. So let us see this. If we consider this reaction with concentrated H2SO4, so let us say we have CH3, CH2OH, that is this ethanol with H2SO4. So we are writing H2SO4 as HSSO4. This is H2SO4. It will first react with H2SO4 to form alkyl hydrogen sulfate, that is C2. This is C2H5 HSO4, and this water will go out. Okay. This is your ethyl hydrogen sulfate, and then if you heat this, then this C2H5 dot HSO4, if you heat this will be C2H4, and from here 1H and HSO4 will go out, so it will be H2SO4. Now let us talk about mechanism of this reaction, because it's very important. So this is our mechanism. See, the acidic dehydration of alcohols takes place in some steps. So our first step is protonation of alcohol. Protonation of alcohols. Alcohols accepts a proton from the acid forming from the acid forming from the acid forming the protonated alcohol, from the acid forming the protonated alcohol. Okay. So this is our first step, that is protonation of alcohol. So let us say we have ethyl alcohol. We are writing in this format. It's our CH3, CH2, OH. So at oxygen we have two lone pair, and we have given H2SO4. So let me write H2SO4 in this manner. This is HOSO2 OH. Okay. See, this is H2SO4. So here what will happen? Oxygen is more electronegative. So it will be delta minus, it will be delta plus. And this lone pair will attack here. Then it will be H C H H CH2 O H dot one lone pair will be there and it will be plus. So it has taken hydrogen from this. This H will be as it is, plus we have OSO2 OH. This whole thing will be as it is with a negative sign. Now our second step is loss of water molecule. Loss of water molecule. So this protonated alcohol lose a water molecule to form the intermediate carbocation, and this formation of intermediate carbocation is a slow step, and so it is the rate determining step. So we have H CH H CH2, then O, the lone pair, H and H, positive charge because it has given one lone pair. So it will be H CH H CH2, and it loses this water molecule. So it will form a carbocation plus H2O. This is ethyl carbocation. Now our third step is formation of alkene. Formation of alkene. The intermediate carbocation just have formed, loses a proton from a beta carbon to form the alkene. Now see, this carbocation is in this carbon. So this is alpha carbon, this would be your beta carbon. So it will lose a proton from beta carbon, that is it will lose a hydrogen. So let us say we have HSO4 minus. Okay, this thing HSO4 minus plus we have this carbocation. So HCH HCHH is the carbocation. Is your alpha carbon, is your beta carbon. So it will lose a proton from this. This hydrogen will attack in this negative charge and this bond will go in this way. So it will be, if H attached, then it will be H2SO4 plus we will remain with HCH double bond CH and H. This is your alkene, that is ethene. This is the mechanism of dehydration of alcohols. It's very important, so be careful. So let us see why this reaction go in this manner. Okay, why the mechanism follows these methods. So our first evidence is relative ease of dehydration of alcohols. This is our first evidence. See, we know that ease of dehydration of alcohols leading to the formation of alkene, as the order is tertiary, is greater than secondary, is greater than primary alcohols. So this is the order of alcohols. Tertiary alcohol will be higher priority than secondary alcohol, then primary alcohol. So on the basis of above mechanism, we can say that formation of intermediate carbocation is the slow rate determining step. So greater the stability of carbocation here, greater the stability of carbocation, the more easily it will be formed, and hence more will be the ease of dehydration. Now, since the stability of carbocation is the stability of alcohols, and stability of carbocation is in the order tertiary is greater than secondary is greater than primary. So tertiary carbocation will be higher, more stable than secondary carbocation, then primary carbocation. So you can say that ease of dehydration of alcohol will follow the same sequence. That is, tertiary alcohol will be prioritized first, then secondary alcohol, then primary alcohol. Now, our second evidence is formation of unexpected products, that is rearrangement of carbocation. So let us say this. Certain alcohols on acidic dehydration yields unexpected products. That is, they yield such alkenes in predominant amount, in which the position of the double bond is not that expected from the structure of the original alcohol. If we take example, butane 1-ol, butane 1-ol on dehydration, on dehydration yields but butane as the major product, as the major product, whereas the expected product is but1-ene, whereas the expected product is but1-ene. So let us see this. Let us say we have butane 1-ol, that is CH3, CH2, CH2, CH2OH. We have this butane 1-ol. If you give H2SO4 with this and heat H2SO4 and heat, one water molecule will remove, and there is a chance of forming two products. One is CH3CH, double bond CH3. This is butane, and this is almost 80%, and this is unexpected. This is unexpected. Our expected product is CH3, CH2, CH, double bond CH2. This is your but1-ene. This is 20% only. This is our expected product. See, our expected product forms only 20%, but 80% of butane is formed, and this is unexpected. So let us see why this is happening. The formation of such unexpected product can be explained on the basis of mechanism of dehydration of alcohols. So according to the mechanism, formation of intermediate carbocation is a slow rate determining step, and the carbocation formed tend to rearrange to more stable carbocation, because we have seen that tertiary carbocation is more stable than secondary carbocation than primary carbocation. So this is the main cause. If the structure permits either by 1,2 dihydrate shift or 1,2 alkyl shift, let us say In this reaction, butane 1-ol on dehydration gives butene gives butene as the major product instead of but1-ene. This is because N-butyl carbocation formed from butane 1-ol undergoes 1,2 dihydrate shift to form secondary butyl carbocation before losing a proton. So let us see. This is our CH3, CH2, CH2, CH2OH. Okay, you are doing it in acidic medium. That means proton is there and it will attach to OH. So CH3, CH2, 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 OH2 plus. Okay. Now after that we will have this water molecule removed and there will be a formation of carbocation. So it would be CH3, CH2, CH2, CH2 positive, and that water molecule is removed. Now the main funda is stability of carbocation. If this carbocation rearranges itself, want to dihydrate shift. So let us say this CH3, CH2, CH2, CH2 plus, and this is your N-butyl carbocation. Here is a possibility of rearrangement, that is more stability of carbocation. So rearrangement, that is here 1,2 hydrate shift is the possibility. So if the carbocation goes in from one position to two position, it will be more stable because at that case it will be secondary carbocation CH3, CH2, CH, CH3. This is secondary butyl carbocation. Now this carbocation is more stable, so we can say CH3, CH2, CH plus, CH3. Now one proton will go away. It will be CH3, CH double bond, CH, CH3 will be H plus. This is butane, and this is your major product. Okay, so this is the main reason. Remember, in case of dehydration of alcohols, you have to see the stability of carbocation. That's all. Let us say, let us see another example regarding this, so it will be more clear to you. Let us say we want to consider dehydration of 3,3-dimethyl butane 2-ol. So let us say we have this thing CH3, C, CH3, CH3, CHOH, CH3. This is your 3,3. Sorry, there will be a hyphen. 3,3 dimethyl butane 2-ol. Okay. Now from this 3,3 dimethyl butane 2-ol, in this case, initially formed carbocation is a secondary carbocation, right? The carbocation will form here. So we are doing it in acidic medium. Let us say H plus proton is there, and it will attach to alcohol. It will be CH3, C, CH3, CH3, CH. This H we are writing in this way, and this will be OH and H with a positive sign. CH3. Here, one water molecule will be removed, and your carbocation will form in this carbon. So CH3, C, CH3, CH3, CH, CH3 with a carbocation. Now this is 2-degree carbocation. 2-degree carbocation, and it is less stable than 3-degree carbocation. If there is a chance of rearrangement, then do the rearrangement. Here 1,2 methyl shift is possible. 1,2 methyl shift is possible. That is CH3, C, CH3. This methyl will go here, and this carbocation will come here. So this will be plus CH, CH3, CH3. Now you can see that this is 3-degree carbocation. 1, 2, 3. This is 3-degree carbocation. 3-degree carbocation. So it will be more stable. And then one proton will be removed. We will have our required product, that is H3C, C, CH3, double bond CH, CH3, then CH3. This is your major product. 3,3 dimethyl but 2-in. This is your major product. Okay. Now regarding this, let's see orientation of dehydration. And for dehydration of alcohols, we have a name reaction, that is Saytzeff'S rule. So let's see what is Saytzeff'S rule. So dehydration of alcohols involves the formation of an intermediate carbocation, just now we have seen, in the slow rate determining step. If a carbocation is such that it can lose a proton from either side, a mixture of alkenes is obtained. So in general, we can say a more alkyl substituted alkene, that is Saytzeff'S product, is always the major product of dehydration of alcohols. So let me write it here. A more alkyl substituted alkene, that is Saytzeff's product is always the major product of dehydration of alcohols. Okay, and this generalization is known as Saytzeff rule or Saytzeff rule. This is Saytzeff or Saytzeff. They are same thing. Same thing. So let us see. Let us understand this topic by one example. Let us say we have butane 2-ol, CH3, CH2, CHOH, CH2, CH3. This is your butane 2-ol. Okay. Now here we are giving phosphoric acid or Al2O3. Okay. So let us say phosphoric acid H3PO4 and Al2O3. Here temperature is 298 Kelvin. That is required. So here two product will form. One is CH3, CH2, CH double bond CH2. This is but 1 in. This product is 24.1%. And another product is CH3, CH double bond CH, CH3. This product is about 75.9%. So it will be more stable. This will be more stable. So in this reaction, secondary butyl carbocation, this will be, if water molecule removes, then this will be secondary butyl carbocation, is formed as an intermediate which is unable to rearrange to form the more stable carbocation, right? If this carbocation goes here, then it will be 1 degree. If this carbocation goes here, then it will be again 2 degree. So कोई फायदा नहीं है. Hence the stability of carbocation does not affect the ratio of the product, but this is your butene product, butene, but butene is formed as the major product because it is more stable than but1 in. However, this is 1 degree, right? This is 2 degree. However, in some cases, the rearrangement of the initially formed less stable carbocation to more stable carbocations takes place, followed by loss of proton. Moreover, if the major product is also capable of showing cis-trans isomerism, then it is always the thermodynamically more stable trans product which predominates. Let us see one example. Here, let us say we have 2-methyl butane 1-ol. We have this CH3, CH2, CH, CH3, CH2OH. This is 2-methyl butane 1 all. So let us give one acid and heat. So dehydration of butane, this is 2-methyl butane 1 all, and from this we will get CH3, CH2, C, double bond CH2. This is 2-methyl but 1 in. This is your minor product, and we will have another product which is CH3, CH, double bond C, CH3, CH3. This is 2-methyl but 2 in. This is your major product, because according to Saytzeff'S rule, more alkyl substituted alkene is always major product of dehydration. Sorry, this would be dehydration of alcohols. Okay, dehydration of alcohols, more substituted alkene. So let me revise once again. In some cases, that is in this case, the rearrangement of the initially formed less stable carbocation to more stable carbocations takes place, followed by loss of proton. And if the major product is capable of showing cis-trans isomerism, then trans product will predominate. So let us say we have CH3, C, CH3, CH3, CHOH, CH3. H2SO4 and heat. And it will be CH3, C, CH3, double bond C, CH3, CH3. Okay. So let us have our final revision about Saytzeff'S rule, or it is also Jet-shape rules. Okay. So a more alkyl substituted alkene is always major product. If you notice here in this double bonded carbon, you have only one alkyl group attached to it. And if you notice here, the double bonded carbon, two alkyl groups are attached. So it will be more substituted alkene. So that's why it is major product. If you see here in the double bonded carbon, only one alkyl group is there. but in this double bonded carbon you have three alkyl groups, 1, 2 and 3. That's why it is the major product. Okay, this is the Saytzeff's rule, and it is very easy to understand. And if you see in this product, you have 1, 2, 3 and 4 alkyl groups. That's why it will be your major product. So Saytzeff's rule or Saytzeff's rule is very easy to understand. So this is all about our dehydration of alcohols. And remember why in the Saytzeff's rule or Saytzeff's rule it is happening, because here most substituted alkenes are more stable due to more hyperconjugative structures. Here you have two hyperconjugation possible. Here you have 6 hyperconjugation possible. So it will be more hyperconjugate structure is possible here. That's why it is more stable. Okay. So I think you have got the point about dehydration of alcohols and Saytzeff's rule or Saytzeff's rule. Okay. So that's all for today. Have a good day.